Hello, guys, and welcome back to the Curious Cube. How's everyone doing?
Hi.
Good.
Doing well.
Pretty good.
You say the same thing every time.
Next week's spring break for me. I'm so glad.
Spring break's in it's in 2 weeks, yeah.
Oh, for you.
For me, yeah, for me.
Because you're in Easter. I'm kidding.
Yes, that's clearly how time zones work.
As a homeschooler, I don't really have a clearly delineated spring break.
Do you get breaks?
It's not just like, there's no official schedule of this is the school, it's looser.
Sure.
So yeah, in this
episode, I don't plan on like going out or anything though. Anyway, continue. Sorry.
Yeah. In this episode, a lot of you have hopefully all seen our Pi Day video from 2 days ago. If you haven't, pause this episode and go watch that one. It's only like 8 minutes long.
Yeah.
And so, Pi is on everybody's minds because, it's March something th. So, we wanted to talk in this episode some about, about Pi and about how, it relates to calculus and how it shows you like good things about calculus. Because
do you want to be more specific?
Okay, so like basically in the math contests that people are used to, like at least the ones that people do in high school, like the AMC 10, the AMC 12, the AMY, the USAMO, calculus, you're not going to just see like evaluate this integral on some contest. There are problems on some maybe contests where maybe there is like maybe on HMMT or something you might see calculus explicitly used or something like that. And maybe there are some Olympiad problems where calculus is very useful, or you might maybe in reality you might use some basic concepts like problem 2 from last year's IMO. Like most of the solutions involve some maybe basic calculus concepts, even if you don't have to like know what is the integral of tangent or something.
I know one of the old math prize problem that like I think technically there's a solution without calculus, but if you used calculus, if you just did a quick integral, then it would like kill it in 2 seconds.
Oh yeah, I think you can technically solve IMO number 2 from last year with calculus, or some other problem where you take the derivative of some polynomial and nice things happen or something like this. But but I think like the MAA's philosophy is that the contests are supposed to have elementary things. And so I guess their thinking is like calculus is a college subject or something. And so like, I guess they don't want to put it on their contests, which is, like that's a reasonable point of view. But it also means that maybe a lot of people who train for math contests are not exposed to calculus as much. And, maybe a lot of you, maybe a lot of you have seen a bunch of, Euler's theorem for polyhedrons, and Fermat's little theorem in number theory, and big theorems in geometry, but you maybe don't know any calculus. And so maybe the first time you'll ever see calculus is in maybe a class that is maybe not designed as much to showcase the most interesting parts, and instead focuses a lot more towards like
computation.
Sure, something like that. And so like
I think it's important to stress that like the MAA philosophy is like I actually think a pretty good one, because it lets people know that like mathematics is not linear, whereas a lot of people who aren't exposed to contests like seem to think
definitely.
math is more linear.
In fact, there's an article you may have heard about this called The Calculus Trap by Richard Rusick, the AOPS guy, who I think he basically, it's something like maybe a lot of people think that if they have maybe young children who are advanced in math, that the strategy, what they should do with their children, maybe they think that it's just, we need to just push our child into the the most advanced classes. They're doing algebra 1 in 5th grade, better get them geometry, and then algebra 2, and then pre-calculus and calculus, better rush to calculus. And so like, yeah, I'm not saying that people should run to calculus. And I'm not saying that the MAA should start putting calculus problems on their exams. Like, it's definitely nice to, like, not intimidate people too much. We don't want the problems to be too intimidating. Like, the ideal Olympiad problem is hopefully simple to state and yet, not so simple to solve or something. But, I'm not saying that the MAA should start putting a bunch of calculus problems on the USAMO.
Yeah, actually, I had like a kind of a. I could very easily see myself falling into the. I see myself having fallen into the calculus trap because when I was back when I was in elementary school, I immediately just got thrown into like higher and higher maths. Just basically just washed along with the school curriculum, which is, by the way, it means well, and I think it's like reasonably comprehensive for what what can be expected of it. But like, I still feel like it's quite constrained. And the first time, and luckily I had started math contests before I started skipping literally everything in math. But my first exposure to calculus at all was, like Luke said, was actually just in a high school classroom. I got thrown into AP Calculus BC, and I didn't really bother to
And you were
learn
how
much
old?
I was in
Like-
8th grade, so like not that tiny.
Okay.
Actually,
So-
that depends on your frame of reference. So I wasn't exactly like. Actually, I don't know. I think it depends on like your school.
But yeah, that's still, like, but I don't, whether you see calculus that young or you don't see it till,
Is it that
you're in
young?
11th grade or 12th grade, or you don't see it until college, which is fine, that's fine. Like, most of you are going to see calculus sooner or later.
Mhm.
And so, like, if you only see calculus from a class, there's a chance you're going to end up thinking that it's, a bunch of compute this integral, compute that derivative, compute this.
And that was much of what my class was, since it was, an AP class. So the bulk of it was preparing for the AP exam. And that is not really built around exploring, cool things in calculus. It was about do this problem but get a 5. And I props to my teacher. I thought he did a really great job of like explaining calculus and like making me at the very least interested in it. But like the curriculum really was not on my side with that one.
Oh, and by
Yeah,
the
what
way,
interesting
sorry,
yeah, what interesting things were you thinking about like showing, for example?
Well, yeah, just as a side note, I want to just mention that even though like officially all the stuff is elementary stuff in the contest, like, it's worth noting that the actual definition of the real numbers, like, this is actually a highly non-trivial issue. This is like not something that people ever actually mention in contests, but like, you can do better than it's a point on the number line. And so this is like actually not that elementary at all.
Wait, I don't think it's worth
Elementary is
I
like
don't think
one
it's
of the
worth like learning until later though.
Yeah.
But like, it's worth
'Cause it's
knowing
hard
that
to
there are more
appreciate.
subtle issues. Yeah, it's worth
Yeah,
knowing
yeah.
that there are more subtle issues. But
the
yeah.
word elementary is, in my opinion, quite misleading.
Oh
in
yeah,
math.
I think the word elementary is used in a strange way in math.
Yeah, I have this book called The Elementary like a friendly introduction to elementary number theory or whatever. It's like friendly, elementary, and then it throws like elliptical curves and the proof to Fermat's last theorem at like the end, and I'm like, thanks.
But yeah, obviously
Friendly.
mathematicians use words in strange ways. If a mathematician, there are jokes about mathematicians calling things trivial or something.
Trivial.
Not trivial at all.
In my old math circle, the trivial was the T word.
One result I wanted to tell people about, because in the earlier Pi Day video, I was talking about how you can write 22/7 minus pi as the area of some region, and that's how you see that pi is less than 22/7. So if you take the function x to the 4th times 1 minus x to the 4th over 1 plus x squared, then you can graph this function, and then like it's 0 at 0 and it's 0 at 1, and it's like positive everywhere in between. So you get some region, and like between this and the x-axis, and you get some region, and this region has positive area, you can see. And it turns out that you can use calculus to see that the area of this region is exactly 22/7 minus pi. And this is an integral. You can use an integral. In general, you can use an integral to find the area under a curve. And this is like an example of, something, from calculus that, is like, even, okay, sure, this is a computation. And in fact, if you're in calculus, if you've done basic calculus, you can try to do this as an exercise. Like, it's actually pretty standard. But, there are other, even if you're just dealing with integrals, like there are other more interesting, there are interesting things that, I think one personal favorite of mine is integral. If you
was it the Gaussian integral one?
Well, that one is good, but the one I was going to mention is of cosine x over 1 plus x squared from negative infinity to infinity.
Yeah.
And for this one, you do a weird thing where you count, if you count things under the x-axis as negative. And so when you do that, and it gets smaller and smaller. So it's sort of infinite, but it gets smaller and smaller. So you can well define this. It turns out that it is equal to pi divided by e, which is I
think
really
you should
cool.
note that it is very difficult to prove without introducing complex numbers.
And this is sort of an advertisement for even higher math beyond regular old calculus, where you can instead of just working with real numbers, you work with the complex numbers. And then if you do this, you get some magical theorems that this just sort of, you get this new integral. And one other result that is sort of, I guess, related to calculus in as much as it involves infinite series, is the so-called Bailey-Borwein-Plouffe formula, which is
Yes, and height.
It's an integral or it's not an integral. It's a sum for pi.
Sum for pi, yes.
That allows you to compute a specific binary digit in.
Yeah, it's pi is equal to the sum as k goes from 0 to infinity of 1 over 16 to the k times something with some fractions. And it turns out that because of these powers, and it works out so nicely that you can use this to compute an arbitrary digit in pi in base 16. You can find a digit of pi in base 16 without having to compute everything that comes before it, which is
that's really
it's kind of this is pretty surprising that such a thing exists at all. In fact, it's considered an open problem whether such a thing exists for base 10. If you find such a thing, you will probably become famous. So that's another interesting thing that, there you can see more stuff about interesting infinite sums and stuff like that, in calculus. And there's more to it than just doing, a bunch of standard calculations. And yes, I should mention the Gaussian integral that Holden said.
Should I talk about this one?
Sure.
Yeah, so the Gaussian integral, it's the integral of the function e to the negative x squared from negative infinity to infinity. So what I mean by this is you can graph the function e to the negative x squared, on your favorite graphing calculator, and then find the size of the region that's below this curve and above the x-axis. And I forgot what it equals already. It was
the square root of pi.
Yeah, square root of pi. Yeah, okay. But the point is that a lot of these very cool integrals actually have a lot of applications as well, because the Gaussian integral, at least the Gaussian function e to the negative x squared, is used to define normal distributions as well, which gives you it's the standard bell curve that you see.
Yeah. Oh, and one thing I should note, I've been talking about integrals to infinity. You can't just automatically define something with infinity. Whenever you're dealing with infinity, you want to be careful and you want to make it more rigorous, because infinity is weird. So there are definitely ways to treat infinity carefully. Yeah, you take the limit as that integral I said of from negative infinity to infinity, you like split it up at some point, like, to go from 0 to infinity, you like go from 0 to n and take n larger and larger, and you do the other direction and add what you get on one side and the other. But yeah, like, there's some book that says like, that compares like e to the pi I plus 1 as being like overrated, and this Gaussian integral with the square root of pi as being underrated. So there's some book that talks about this, and I definitely like, I think I would agree probably with this book. Like, it's.
Do we want to move on to the next question at some point?
Yeah, I guess that's enough about calculus for
Yeah,
for
yes,
now.
yes.
But
Especially since like a
please
lot
don't,
of
please, yeah, please don't be scared by the notation or by the weird, computations. Like, this is something that you can learn, and you can see lots of like neat things. And also, the history of calculus is a whole separate issue, which is
I like to think
totally
of it
beyond the scope of today's episode. But you should read up on it. But yeah, I think that's enough about
I like to think of
calculus.
an integral as like a sum, as like basically just sigma notation, but cool.
But yeah, so I guess we will move on to something that so I guess we will move on to an actual like question from the audience, which is, someone was wondering, what is the first Olympiad problem that you ever did?
Should I go first, I guess?
Sure.
Yeah, so the first Olympiad problem I ever did, if I remember correctly, was in high school, my freshman year. And I signed up for this program on AOPS called WOOT, which stands for Worldwide Olympiad, or Worldwide Online Olympiad Training, or something like this. And in this training program, they give you practice tests. And I was bad and then didn't do the first practice test because I forgot it existed. And so I think like the first problem I ever solved was the first problem on the second practice test. I don't remember what it was, but it's that one.
Did you have any like particular feeling as you solved
No,
it?
it just felt like an Amy problem. I think that's the intention too.
Oh, that makes sense. My first Olympiad problem was literally in contest. It was the math prize for girls Olympiad 2018 number 1. I remember I know it's kind of weird. My first one being literally like during it. The idea was I qualified for the Olympiad after the 2018 math prize for girls, and I completely forgot that there was an Olympiad until I got called into until like I got told like I got told like the night before, and then I got called into the counselor's office the next day because she was proctoring me. And then she just handed me the problems and a lot of scratch paper. I just stared at the problems. I was gonna like just turn it in because I was like, I've like never done an Olympiad problem before. But then I just like started playing around. I ended up solving it. So worked well in the fine. Worked fine in the end.
Yeah, I mean, in my case,
you have to remember yours.
I mean, well, I remember some old Woot. Like, I also did Woot when I was much younger, though. I don't know if it was like the first problem I ever did.
Holden and I be doing it in. I'm pointing the wrong way. Holden and I really did it in our freshman year, and then Luke is
like here, like it's maybe it was some problem on some Woot Olympiad, but also like I think what Holden said about it just felt like an Amy problem is like there's a point that Evan Chen has talked about, which is like that there's not actually as much of a difference between like there's not that big of a gap between like short answer problems, like maybe the hard end of Amy was what he was talking about or something, versus like easy Olympiad problems, like easy problems that are easy as Olympiad problems go, not that they're easy in an absolute sense or anything, but like that there's maybe not that big of a gap in as much as like in some ways in that like you just have to explain your solution And like, if you're just, so in some sense, like when I was going to some math circle when I was younger and presenting some solutions to some problems, like you could argue that maybe those are practically Olympiad problems. Like, you know, so relatedly, like, you know, maybe people don't need to feel, I mean, like you could, you know, like you don't need to feel like something, like you don't need to feel like doing an Olympiad problem for the first time is like some, you know, impossibly big gap. Just like keep doing problems, and like if you treat problems as if they were like problems on a contest where you had to write things up, then you're like practically doing Olympiad problems already. Like it
There
doesn't
aren't that
have to,
many contests that have that, to be fair.
I mean, there is, well, there's, you know, USAMO or JMO, there's
No, no, I
USAMTS.
mean like problems or contests that have you show your work. I know there was one that I did when I was younger, but that one's kind of is not. It's like more of a local thing. I do have a funny anecdote though. The first time I ever took the math prize for girls test, my dad somehow convinced me that it was also one where you had to show your work. I think he might have been trying to get me to show my work when doing practice problems. But as a result of this, like I go into the contest, and the way they give you scratch paper, they don't actually give, or at least back my first time, they didn't give like a stack of scratch paper. They literally gave you like a little booklet of like lined paper. And I was like, okay, it looks like it's time for me to write up my solutions. So like every time I finished a problem, I would just like slowly and meticulously write that up. And and
That
then like at
seems
the end
like
of
a
the
way to not get a very good score.
it was my first time, so like it wasn't like I was expecting anything. So I would like meticulously write it up, and then at the end of the test, the proctors come around and I'm like, here's my solution packet. They're like, oh, it's just your answer sheet is fine. I'm like, what?
Oh,
That
and
must
like
be
I want
hilarious.
to just to be clear about that, like that phrase "show your work." I think like maybe people are used to tests where they have to like actually show every step of how you solved a problem. On an Olympiad, it's not like that. You know, you can just, the solution to an Olympiad problem needs to like explain why like you need to explain why the solution is correct, but you don't need to show why you came up with it. It can just like, you can just sort of see it. It can just click. You can just have an aha, and you have no need to explain any of why that comes to you. You can just, you know, and I
Yeah,
mean
you
there
don't have to
are
explain
some,
your motivation.
yeah, you don't have to explain the motivation. I mean, there are some contests where there are some very high level contests where you do submit your scratch paper, but that's beyond the scope of this episode, I think. Don't
I
worry
think a
about
good
that.
heuristic is like write down enough to convince the grader that you actually know why the problem statement is true.
Yes. But like you don't have to, you know, just like write the mathematical proof, but no need to like, you know,
I guess
no
on the
need to
topic of first
explain
Olympiads,
why.
like another,
No, like no need to explain why you thought of it.
yeah. Yeah, on the
Well,
topic of first Olympiads, I think like a more memorable first problem that I did was like my first in contest problem, which was 2018 USAMO #1. For people who don't have Luke's memory, this is a 3-variable symmetric inequality that had a minimum function in it. I don't remember the exact statement, but it was like that. And then I went into the USAMO not like expecting to get anything. And for the first 2 hours, I like didn't get it at all. But then eventually I like found this miraculous like factorization, and then it somehow worked. And when I wrote it my solution, I like didn't know how to write it up, so I just wrote it up in 2-column proof style. And like when I solved the problem, I homogenized the, or I like unhomogenized the inequality to make it easier. But I didn't realize this was an actual thing you could just write down in your solution. Like we like without loss of generality, assume ABC equals 1 or whatever. So I just like wrote down the entire solution unhomogenized, or like sorry, like without you know what I mean, right? And then I also didn't know you could just say without loss of generality, assume the minimum of these 3 numbers is the first one because it was symmetric. So I just wrote the entire proof 3 times. Do you not know this?
I don't think I knew that much. But yeah, this is like another like thing. Like this is sort of brings us to this is like ties into the next topic of this episode, which I guess we've all sort of already moved on to, which is like the USAMO is in like less than a week, or USAMO and USAJMO is in less than a week. And so like probably there are quite a few of you who maybe are going to be taking this contest for the very first time, and maybe quite a few.
Congratulations.
That's yes, really congratulations to everyone who like is taking this test.
Mm-hmm. It's a really big deal.
Yeah, and like congratulations if you even if you didn't make it, like congratulations on even trying the Amy, and congratulations even if you tried the AMC 12 or 10 and didn't make the Amy, but for the people, probably some of you are taking this contest for the very first time, and maybe you want some advice from us. And so like this is some of it I guess we've already said, but like in relation to something Holden said, like the proofs on these contests, it's not a 2-column proof. No one uses 2-column proofs in real life.
Rip Holden.
Yeah, like no one is like, they're not going to mind if you write a 2-column proof. Like you're not going to get points deducted for writing a 2-column proof, but it's a waste of your energy to write it as a 2-column proof when you could just like explain it with words, like you're just like as if you were talking to someone, like in sentences, and with equations as necessary, So yeah, like
on the flip side, I heard I heard like I heard from somewhere, I'm not sure exactly where, of USAMO and JMO being described as contests with answer form with the contestants being required to write essay form. And that just brought the imagery of someone just writing like a whole persuasive essay about like why their proof works. So don't go too many words, otherwise you'll like
like the proof is as long or short as it needs to be. If the whole argument, if you solve the whole problem, like if you can explain the whole thing in 1 page, great. If you need to explain it, if you need to take 10 pages or more to explain it, especially if you have large handwriting like I do, then like go ahead, take all the paper you need, even if it takes 20 pages or whatever. Some of you have larger handwriting than others. I have unusually large handwriting. But yeah.
I think one thing that's
also, your graders are not dumb. Like they have seen the problem. They know how to do the problem. Like
they want to be convinced that you know how to do the problem.
Yeah, they know math. They are very good at math.
Yes.
So you don't have to explain like every little thing. Like what are congruent triangles?
Yeah,
I think one thing that's really important to stress, especially for people doing an Olympiad for the first time, is like use English and write in complete sentences. In particular, write in a way that like if you were explaining the problem verbally to someone, as in why the problem is true or why you think a statement is true, just like write down word for word what you would verbalize. Because too often when grading, I just see like sequences of equations and I don't know what's going on.
Yes, use words. Words are good.
Words are good. It's just, you don't have to make yourself too long-winded.
And so another thing, what was I gonna say?
Back to the paper point. If you thought Amy was the contest to kill trees on, wait till you see the USAMO. Holden had this whole thing about rewriting his proof 3 times. I had that in 2019 Math Prize Olympiad, problem 1. Like I kept doing the problem over and over and over again, and I would like flip something, and I was just doing something wrong. Like sometimes I would think I had the solution, but then I wouldn't have the solution, so I'd have to do it all over again. And oh my gosh, I went through so many answer sheets. I think it was like I had to ask for more copies, and I think I went through like something like 30 sheets or something.
Yeah, like and
Luke goes through more.
Yeah, use a bunch of paper now, and then like donate to environmental charities later.
Usually, I only use one side of the scratch paper just because it's easier to organize, and then I like. If I could save it, I would save it and then just use the back side for later scratch work.
Yeah.
And going back to the issue of like, people taking an Olympiad for the first time, like maybe some people, like, people who are inexperienced, like probably do not have, much knowledge about how much detail they should or shouldn't include. So some things are like, as Holden said, it's this, a good standard is like, you want to convince the grader that you have solved the problem. So you want to like include enough detail so that the grader is convinced that you solved it. So some things this means is like, if you're citing a result that is well known, like if it's super, like, if it has a name, say the name. So like if you're using AMGM, say that. That's the inequality of arithmetic means and geometric means, if, for people who don't know. Or, if it is well known, but you're not sure if it has a name, like say that it's well known, give a reference if possible, like, oh, this is in Evan Chen's book, and maybe like, maybe give an outline of why it's true, at least like, at least a sketch of why it's true, if nothing else, because like, like you could just like, if you say something is well known, you might actually know that it's well known and just not know the name of it, or you might just be bluffing and hoping that the thing is well known.
Yeah, you want to convince the grader you actually
so like if
know.
you give even a sketch of the proof, it might help. I mean, and if you have time, you can just write out the whole thing, but
Treat as
even
a
like a
lemma.
sketch or something. Like as an extreme example, on the IMO, well, actually, without going into too much detail because I don't want to spoil the problems, but on a recent IMO, there was some case in which you could, you trivialize a substantial portion of a problem by using a known theorem whose proof is like not easy. And it was literally like, it was a special, in this case, it was like a special case of a more general theorem. And like students had to show that they knew either that they knew the more general result or like literally give the name. Like literally, if someone just said, oh, this is well known, then they would get not the full credit versus saying, oh, this is so-and-so, this is well known by name of theorem. Like they got full credit. Like this is, or at least according to the rubric. Like, and this is an extreme case. The ideal for math contests is that you don't want to have too much dependence on known theorems because, you want it to be more about creativity than about how much have you seen. And you especially want it to be more about creativity than about, let's have a trivia contest. It's time to play Theorem Jeopardy.
Oh, yeah, I think this is a good important point to emphasize, right?
Wasn't there that one USAMO problem
Oh.
that was like a specific case of like some theorem?
The hook length formula.
Hook length,
Yes.
yeah.
Which
Yeah, that
was
was
like,
not
I was
good.
like,
So
I was
this-
like, it's hook something.
yeah. So yeah, obviously what I was saying is like they want it to be more about creativity and good ideas than, you don't want it to be all about let's play Theorem Jeopardy. But this does happen. Like in reality, it happens. And so, one good thing you can say about like if you want to cite a result, you should actually like state the result you are citing. Actually, I mean, okay, if it's super well known or something, you can just give the name but like if you're citing a less well-known result, it might be a good idea to like not just say the name, but it might be a good idea to actually like say the result to like really prove that you know exactly what it is that you're citing.
Oh,
But
also,
maybe
you
this is
mentioned,
too
like,
much talking about like theorem citing. We should,
Yeah.
I
Also,
think like the last
you guys talked about an Olympiad rubric, and like some people don't know that this even exists.
Oh, right. Yeah.
oh yeah.
We should be clear. Like on an Olympiad, the point is not just to generate like a bunch of work on like special cases. You want to like actually fully solve the problem. Like if you've just generated a bunch of work on special cases or something, like, you very like the keywords are like non-trivial progress. If you like have actually like gotten at least a first step to the solution or something, like maybe that will give you points. But if you just did a bunch of special cases, like, that's like you might get a 0 on the problem.
Whereas you'll probably get a 0.
Yeah, like, it's not like a bunch of partial credit being handed out. Now there is partial credit, but like you don't just assume that you get partial credit for like everything. You really want to fully solve the problem. And that's another thing. Like sometimes people don't give enough detail for things, especially on combinatorics problems. you should like be sure that you can give enough detail, because like if you can't give enough detail, you know, maybe the reason you can't give enough detail is because it's wrong. Imagine someone like looking over your shoulder and I mean, I don't know how helpful this is to say, but like imagine someone is asking you like, can you clarify that more, and like be more rigorous, because like especially
Imagine a little kid asking you why at every step.
Like especially sometimes people like to say, like sometimes on combinatorics problems, people just like assume that something is like the best case or the worst case, or like clearly in the optimal case we have to do every blah 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 or something. Like you can't just assume things. You have to like, if you said something like, you know, you really have to be careful about not just assuming things, because you haven't, you know, you really have to be sure you've covered all the possible cases. And you know, if you're tempted to use the word clearly, like you might want to double check and ask yourself, is this really clear? But going back to the thing about partial credit, there's one other thing that should be mentioned, which is that some Olympiad problems have sort of two parts to them, in the sense that it's like find all not so much that as things like find all possible values of blah blah blah, find the smallest possible value of blah blah blah, find the largest possible value of blah blah blah. And so like often for such problems, you maybe have two parts where it's like, you know, if it's like find the smallest possible value of such and such, it's like, oh, there are two parts. Show that, like, okay, say that I want to show that the smallest possible value of x is 105 with whatever the rest of the problem is. Then like there are two parts. You want to prove that x can be equal to 105, and you want to prove that it can't be any smaller. And so sometimes
some people forget that first one.
So yeah, you don't want to forget the first part. You want to remember that. This is something Evan Chen has written about. But also, this is a way to get partial credit, because maybe the getting one part is easier than getting the other part, and you can maybe get 1 point or 2 points for just like getting the one part of it. But you want to be sure, like, you know, you want to actually like give enough detail. Like last year on the USAMO, there was some problem about like find all possible values of n such that some certain thing is achievable, and it was like the easy part of the problem was proving that some certain values worked, and the hard part was proving that other values didn't. But like if you're trying to get the points for like the easy part, actually do the whole thing. Don't just say these are the values that work, I'm done, and not write anything else. Like these are the values that work, here's why they work. And that, I think that actually was worth a point. And I got a point on that problem, even though I didn't figure out the hard part. And a lot of other people also got a point on that problem.
Wait, which problem was this?
Problem 3.
Okay.
I think above all, especially for first-time takers, just explore, try everything.
Yes, you know? And also like something like the problems are supposed to be in difficulty order, but something Evan Chen has talked about is like, and something that is very true in real life is like the problems are supposed to be in difficulty order, but difficulty can be personalized, and also sometimes the organizers just get it wrong. So like problem 3 might be easier than problem 2. Problem 2 might be easier than problem 1. Even problem 3 might be easier than problem 1 in extreme cases of the organizers really getting it wrong. Or it might be easier for you. So like actually try all 3 problems at least a little bit. And like, you know, don't go into the problem thinking that there's just no way you can possibly solve it. You know, like you want to try approaches that actually might give you a solution. Though it's also good to just like try understanding the problem a little. You know, it's a hard balance, and you don't want to go too far down one route. But anyway, I think we're sort of approaching the time that the episode should end. So
yeah. So for those of you once again, for those of you taking the USAJMO, congratulations for qualifying and best of luck.
So yeah, good luck to all USAMO and USAJMO takers, and stay tuned for our next episode in 2 weeks.
Yeah, we will see you next time. Bye.
We finally did an episode shorter than the one before it. Bye.